Hello, hello, hello. This is section 7.3, part B. This is going to be the last section from chapter 7 on sampling distributions. We're going to look at sample means again, but specifically what's kind of a combined distribution or difference in sample means specifically today. So let's start off with an example that you can answer based on what you've already learned. I've got two scenarios, the heights of 10-year-old girls and the heights of 10-year-old boys, and we're going to compare the two. But for each one, I'd like you to look at if we have, let's just say, an independent simple random sample is of 12 girls and 8 boys, and we measure their heights. I would like you to describe the distribution of each. All right, so take a moment to do that. If you want to pause it and do that, this is a good recap of what we learned last time. And let's take a look at what you should get. So from that information, both shapes are going to be approximately normal. We know that because it wasn't because there was a large enough sample size to say that it was the central limit theorem, but because the population distribution was normal. That means that the sampling distribution will also be normal for both. So we can say approximately normal for both. Now the center for the girls, it's going to be the same as the population height, which is 56.4 inches, while the center for the boys is 55.7 inches. So at about 10 years old, girls are typically taller than boys. Now, standard deviation, it's not the same. It is going to be sigma divided by the square root of n, because we have this sample of 12 or 8. So that gives us, for girls, the variability was 0.78 inches, and for boys it was 1.34 inches. And we can assume that they're independent because, actually it did say independent, I think, samples, but we can say that 12 is less than 10% of all girls in the United States, and 8 is definitely less than 10% of all boys in the United States. All right? So we're going to use that information, and we're going to compare some things. Because now that we have all the information, we can compare them. So let's just say that we asked the question, what can we say about the difference between, and this is for girls and boys, the mean difference between girls and boys in this sample. So girls minus boys. Well, over here we have a whole large set of samples. And they're shown on this distribution on the right of this dot plot, which, if you look at it, it looks fairly normal. We have one red dot down here, and that's just to note, that's representing a set of samples that gave the mean girls height of 56.09 and the boys height of 54.68, resulting in a mean difference of 1.14. Now, if you think about it, if we go back to our averages, 56.4 and 55.7, that's, what is that, 0.7 inches? So on average, they should be, girls should be about 0.7 inches taller than boys. And if you look on this dot plot, where the center of it is, it's somewhere in here, which is probably around a little bit less than 1. It's probably at that 0.7 inches. And why does it make sense that it looks the way it looks? Well, we know that both sampling distributions were going to be normal, so if we combine them, if we do subtraction with both of them, that's going to result in an approximately normal distribution. And those are just a couple of things that we're looking at for a difference in sample means. Now, when we find the mean, we kind of found the mean difference. It's going to be just subtracting the two right here. We find the standard deviation. Remember, with a combined distribution, that's a different formula. But we can put together what we've learned now, and we can make that. And let's do that here. Sorry, that's a little bit smaller than I expected, but we have this information. Why does it make sense that it looks approximately normal? Well, let me fix it. Well, normal minus normal is going to be normal. As long as we know that both distributions are normal, we'll get a resulting normal distribution. The center. So if we said the center would be the mean of the two differences, so x bar of girls minus boys, it should be 56.4 minus 55.7. which should get us 0.7 inches. That should be our mean difference. Variability, so sigma of the differences, now this is a combined distribution or a joint distribution. So we have that formula, the square root of, this plus this, the two variances added together. So in this case, we'd be taking what we found for those variances of 2.7 over the square root of 12, which we did get an answer for, and we'd be squaring that, plus 3.8 divided by the square root of 8. We'd be squaring that. Now, if you think about it, that does get us, like if we wanted to distribute the square, we could distribute here, and then we could cancel out that, distribute here and cancel that. So we don't have any parentheses, we don't have any square roots on the bottom. It's rationalized. And that's ultimately what we're going to do with the formula. But for just finding it, we wouldn't have to do that. We can just find those values, which we actually already found. But this gets us about 1.55 inches. That's approximate. But that gets us the approximate mean difference. Okay? The variability for that. So ultimately, something that's on your formula sheet that's given for the AP exam are these formulas for difference in sample means. But here they are. You can write these in your notes. So if you choose a simple random sample of size n from population 1 with a mean and standard deviation, and an independent simple random sample of size n from population 2, same deal. We can assume, step 1, shape. We can assume that the shape is approximately normal if both samples are approximately normal. So either if we know that their populations are normal, or if we have to use the central limit theorem, that's something we can also use. That's the only thing we can tell about their sample shape. The mean difference is just going to be the same thing as the difference in the two population means. And the standard deviation, we just talked about that. It's going to be the square root of, now you can see here, this is, like it was all of this squared with the square root over here. But then when you distribute it and you cancel out this square root, you just end up with what's left here. So that is ultimately our formula for standard deviation. And that works as long as the 10% condition is met. For both. It has to be checked for both. Okay? So let's now look at an example or two that deals with a difference in sample means. So we got a family size cereal box. So a Fruit Loops contains an average of 21.5 inches of cereal with a standard deviation of 0.2 ounces of cereal. And a large, because they have all the different sizes of boxes, family size, large size, mega size, whatever. We're going to compare the family size and the large size. The large box contains 13.5 ounces with a standard deviation of 0.15 ounces. 35 family size boxes and 40 large boxes are randomly selected, and the amount of cereal in each is measured. So just to summarize a little bit here, it might be helpful to reiterate. So for a family size, there's an average, so a mean, we'll say F for family size, is 21.5. The standard deviation of the family size is 0.2. And the N, since we're going to be using N a little bit here, we have 35 boxes we're looking at. From the large, so the mean of the large is 13.5 ounces. Standard deviation of the large is 0.15 ounces. And we have a sample size of 40. So describe the sampling distribution of the difference from family size minus large, the difference in those two. I just want to make note, at this point we don't know anything about the shapes of the population distributions. So if we don't know that, then we're going to have to look for the central limit theorem. So if I wanted to do this, definitely if I'm describing that, I'd probably put some context to it, and I'd say the sampling distribution of the mean differences between family and large size cereal boxes is blank shaped with a mean of this and a standard deviation of this. So I'm going to make note, add context, but I want to make sure we understand the three things we're looking for. It is SOC V without the outliers because it's not going to create any outliers. So we need the shape, the center, and the variability. So for the shape will be approximately normal, but why? It's because both samples, holy spelled samples wrong there. Let me fix that. Both samples are greater than 30. We had 40 and we had 35, and that's the central limit theorem. As long as we have sample sizes greater than 30, we can assume that it's going to be approximately normal. The distribution would be. So since both of them are, then the combined distribution will also be approximately normal. Let's go to the center. We want the mean. And that would be the mean difference. So the mean of the difference between the family size and the large size is going to be the difference between their two means. So really it's 21.5 ounces minus the 13.5 ounces, which gets us 8 ounces. That is our mean difference. Now for variability, we're looking at standard deviation. And that's what we also just talked about the formula for. So the standard deviation, we'll just say family minus large, would be the square root of sigma squared, so that's 0.2 squared. That's sigma squared from the family size divided by the n value plus sigma squared of the large size divided by its n value, which was 40. And if we do the calculations, that gets us approximately 0.0413 ounces. Okay. Now, I want to do one other thing there. Because we're doing the standard deviation, we should be checking the 10% condition. All right. Is 35 less than 10% of all family boxes? And is 40 less than 10% of all large boxes? I would say we can assume yes for both of those. Because they make a ton of boxes. They might even have that many in one store. So we're going to say yes to both. But we want to state that, we want to check that, and make sure that we can actually do all of what we're doing based off of the conditions being met. And there's our context, or there's our distribution. So we're able to describe the shape, the center, and variability, and we can add some context to that. Now, if we wanted to interpret something, I want to show you, like, this is worth writing down. We've done this. We're just kind of putting it together with the difference. So if it says interpret the standard deviation, we can say the difference, and I'm going to say, specifically say the direction. This is important to state the direction. It's family minus the large size, as opposed to large minus the family size, because that is important. So the difference in the sample mean amounts of cereal typically varies by about 0.0413 ounces from, oh, I have ounces on the next slide, ounces from a true difference in means of 8 ounces. Okay? Very similar to ways we've interpreted in the past, just stating that we're looking at the difference now. So one follow-up question then. Find the probability of getting a difference in sample mean that's less than 7.9 ounces. Now, because we already set this all up, now if you were just asked this question, you'd have to set up all the information, make sure we know that it's approximately normal, figure out the mean and the standard deviation. But because we already did this, it's going to be an easier question. Okay? We are looking still for that difference in sample means, and we said the mean was 8. We said the standard deviation was 0.0413. We have all that done already. We're looking for the chance of getting less than 7.9, which also is kind of wonderful because it's just less than, which is how our table of values works for z-scores. So as long as we can find the z-score for 7.9, you get approximately negative 2.142. Go to your table. The probability of z being less than that is 0.0078. All right, so there's a 0.78% chance of getting a difference in sample means that is less than that 7.9 ounces. It's not real high chance. So with the fact that we have so many samples, it makes it pretty tight around that 8 ounces. It's going to be very close. There's not a lot of variability. And that makes it such a low percent chance of getting even just off by 0.1 ounces. And that's how we can work with difference in sample means. Again, it's very similar to what we worked with sample means, and also similar, but probably slightly easier than sample proportions. But that is section 7.3b, difference in sample means. We'll see you next time.